righty. Well, I guess I apparently am in the last one, and I'm delighted to see that there are still a lot of people here, and I'll try and make it worth your while to stay and keep it lively. So, I'm not sure if that's my. Oh, here's my. There we go. Um, oh, that's the next slide. I got it. So, my motivation for the study I've done, doing thermal inertia as a means of determining soil moisture. Well, my first question to my dad, who never missed an opportunity for a teachable moment, was, Dad, why aren't we going to the beach today? It's 90 degrees. And he said, well, it's June and Lake Ontario is still 55 degrees. We can't swim there. So then he explained it to me, and that's kind of stuck with me ever since. And that's been I can't even calculate. I need a calculator how long ago that was. Additionally, when I was getting started in my career in the early 80s, I was really a pure hydrologist. I realized that soil moisture was an important factor, often almost the most important factor in everything I was interested in. Flash floods, non-point source pollution, source areas, variable source area hydrology, on and on and on. And you all know that. In fact, I appreciate that several the presenters ahead of me also said the same thing. And also about that time, people were really starting to tune into Landsat and felt like remote sensing and hydrology was really going to be a thing. It was too early, though. It's not too early anymore. So what's the context? Anyway, I want to this the context of this, and I think this is something I actually made this slide yesterday, something that seems to is evolving over the course of this workshop is the whole spatiotemporal issue around soil moisture and what spatiotemporal scales can we deal with? Resolution, size of a data set, um, and the temporal resolution. How frequently can we update the data? And clearly, global scale on a weekly basis. Seen that on the screen many times and very useful for strategic purposes, for planning, for long-term trend analysis and stuff. And I've also seen some incredibly good work and learned an awful lot about sensors, in which you could have minute by minute. I'm sure usually it's 15 minutes or an hour, but you could have minute by minute high quality measurements at a single point. Well, there's a whole range, there's a whole spatiotemporal range in between there. And one in particular is one that I kind of feel most interested in, so to speak. That would be something like a daily 30-meter resolution. And that's really what one would be looking at if you're thinking about trafficability, and not always military vehicles, but it could also much more likely be farm vehicles and flash flood warnings, irrigation issues, timing, um, placing of firefighting resources. Where do you want your team? Should they be in this county or this neighborhood? Every minute counts. So, and another thing I've discovered, I guess I knew this, I was getting this impression long ago and reinforcing it today. There's no one single technology or method or idea that's gonna help us get soil moisture, period. There's all kinds of different ways. We saw SAR, latent heat flux. I've seen a lot of different looks at the whole thing. And the key is that not any one of them is ever going to be able to do it. However, putting them all together and looking at them in a kind of a uh, combined scenario of sorts will lead to an answer. Sometimes it's called downscaling. I suppose you could think of it as upscaling. You could think of it as filling in the middle. So I think that's why it continues to be important to think about all the different methodologies, including using thermal data, thermal inertia analysis. So goals of the presentation. I'm early in this work. I've only just this year decided that this was going to be the thing for me. I don't have a full-time research job. I have a class that's 3 times this size, which takes a lot of my time. I'm actually very, very interested in any sort of collaboration. And I promise you, the way I view what's coming up, what I'm going to show you is it's like you're at the gates of Disneyland, the front entrance of Disneyland, and you know it's all wonderful in there, and you love to share it with other people, and everybody else tell you which ride is the best one to go on, and etc. So think of it that way, and I'm really, really very anxious to collaborate in any way. Minor collaborations, grants, talking to your grad student, whatever it might be. And today I'd like to also convince you that this whole thermal inertia thing is entirely viable, that there are tools for machine learning and workflow managers, I'll mention that in a few minutes, that allow us to take varied large amounts of data and do something with them. And finally, I believe that there's enough data, mainly from instruments and point locations, to train a machine learning model. And there's enough remote sensing data to actually feed that model once it's been created and trained. So I think we're in an extremely good place for working with soil moisture. So I think I'm already way slower than I thought I was going to be. So you probably all know what thermal inertia is. I already told you about Lake Ontario. Water has a very high heat capacity. Also, water has a very high thermal conductivity. And so, you know, Lake Ontario is easy. It's uniform in every way. It's all water. Soil isn't. Soil contains solids, air, water, etc. And as water moisture content increases, thermal conductivity increases. So in the general frame of how fast soil changes temperature, these two work against each other. And I'm going to take half a minute on this busy slide right here, which explains all of the hassles and why this problems that I first saw in 1982 still has a ways to go. Lots of complications trying to find an analytical closed form solution to how do we convert thermal inertia and soil moisture and put those together. So what do I suggest? I think an empirical approach is called for in this matter, not a entirely analysis driven. Analysis is in the sense of analysis like calculus and such. Rather, an empirical approach is useful. And the data that's available, it's all over the place at incredible resolutions, like one would never see before. So there's a little flash slide about all the great data that's out there, spatiotemporal, and that's important. Additionally, there's this wonderful international soil moisture network, which actually a cornerstone, of course, is our climate reference network, which has the best stuff. I believe there's some wonderful stuff. The International Soil Moisture Network, another ingredient in my whole idea analysis here, is that it has a wonderful API. I mean, not only is that 38 gigabytes of data, just an enormous amount, but it has an application programming interface, which makes it very easy to extract, manipulate, and work with all of the data in there, and that can be used inside the Google Colab Python environment. And everything I'm talking about today is free. That makes a very big difference, except for one thing, and I'll complain about that when I get there. Everything in this is free, so one does not have to have enormous amounts of money. And another reason I admire all the instrument people for finding your $1 million to put in a whole nother network and such. That's invaluable. So using the API, came up to that, using the API inside of the Colab environment, it's very easy to drag whatever information you want out of that data set. And here's just a quick graph generated for 10 days in one place. And if you look at the blue and the green, you can see there's a 2 or 3 hour lag, and that's all expected. That's undergraduate level stuff, and the soil moisture. But it's all in hand. So what do we do with this? Well, in place of formal mathematical thermal inertia measurements, conductivity and such, perhaps we can look at the apparent thermal inertia parameters, and that would be time lag. And additionally, the response ratio. If the temperature moves this much, how much does the soil temperature move? So if we compare the soil temperature and the air temperature, we see the same lag. It's a few hours. The soil can't keep up warming up, can't keep up cooling down. That's an important parameter. And so then, whoops, next slide. Then for a single site in Ithaca, where I spent a third of my life, I think, or a quarter of my life. I just picked that one, random otherwise. So just for Ithaca, this whole thing is able to give us two different empirical measures of thermal inertia, two simple ones, just for a beginning, and the soil moisture that was present when each of those lags happened. And for Ithaca, there's 92,761 days of that. And actually, that means you have a lag at the peak and lag at the trough. So that's a lot, but that's not all. There's also 124 more stations just in the US that have everything. There's many more in the Sierra that lack a couple things I might want, but there's 125 with everything. Not just these thermal inertia things, but every property of the soil and environment at that location that might influence the relationship between the thermal inertia and any of these parameters, or the thermal inertia and the soil moisture. So we have soil type, which of course has 20 or more parameters of importance. Climate, land use, etc. Latitude could even be a difference. And another nice thing is the API that comes with the International Soil Moisture Network also allows one to relatively easily, wrangle all of these data as well. So you could build a data set of astronomical size. And so how does one deal with this? Well, machine learning is one way to do it. And if you take a snapshot of this, there's an hour's worth of videos that explains it beautifully. So I won't try. We've all seen this diagram before, and it's called it's deep learning or a multi-layer perceptron. Greatest sounding term. So anyway, this is one tool one can use to take this massive amount of data and try and make some sense out of it. Machine learning has advantages. Unlike straight up statistics, nonlinear relationships can be dealt with. Variables that are not independent of each other. That's a big no-no, when they in your undergraduate math and statistics. But machine learning can deal with that. Machine learning can handle numerous variables as well, and conceivably we could have 20 variables that establish the relationship between between thermal inertia and soil moisture. Once a model is trained in machine learning, they can run remarkably fast. So a trained model can be a real-time application. And what else? Oh, there's something called SHAP, which was the final ingredient that convinced me that machine learning was okay. Machine learning does not have to be a black box. SHAP is a way you can generate a set of tables and values which help you to interrogate the interior of that model so that it's no longer a black box. You can see which parameters have the most influence and all that stuff. So it doesn't have to be a black box for 5 years or 8 years. It's a black box. Stay away from that machine learning, but it doesn't have to be. So what is a way, and this is just a little tidbit, sometimes a byproduct of a project or a talk it could be as valuable to somebody as the theme of the thing. There's a tool called NIME, which is a acronym of a German term, and it's free. Everything's free, and it actually is a workflow manager, a data science application, in which you can do an awful lot of very powerful things very easily, managing your data. And this here, the elementary school color boxes and arrows here are a complete machine learning model which takes some data that from Ithaca for one little snippet of time and models soil moisture versus the time lag between peaks. So so that is a complete machine learning model, which shows you don't have to have your computer science professor work full time along with you to write this, and also you don't have to worry about what files came where and what data, what file goes into another file, etc. Lest you worry about the availability of data to employ a model once created, I just put this up here. That's Pluto. And that's Pluto at a 30-meter resolution. And that area is only like 8 miles across. So if we can find data of that accuracy and quality, or it detect that on the surface of Pluto, a billion miles away or something, we can find very good data on Earth. And one very tempting or possibility is a new company called SatView. They call themselves the world's thermometer, and they have a whole is it a fleet? It's a constellation of satellites up there measuring surface temperatures on a 20 times a day around the whole world. And so it's like I'm still looking for the catch, besides the fact that it's currently very expensive. But it does measure surface temperatures at a 3.5 meter resolution and at a very, very frequent basis. This shows Las Vegas, and you can see the blocks. And if I can look and see individual houses, and you can see the temperature differences. And moving ahead, zooming in a lot. Yep, every cell's 3.5 meters. So there is data. There can be. We can get that. If I can show you this, if I can show you the surface of Pluto, it will be possible to find, maybe not today, but definitely it's not science fiction, that we'll be able to get very high resolution thermal data to feed a model which has been built on top of these wonderful soil moisture networks. And that is it. Not too bad. I was only a little off. Anyway, whoops. Oh, I can see the next slide, but you can't. It's a cartoon. Anyway, here's me. And I'm probably the last one on the list if you publish a list. And I'm very, very anxious to hear from anybody. And it's like, what the introducer to our session, you said it's a success if you can make a couple of new friends. I'm hoping for a success in that matter, as well as learning some new stuff. So take a snapshot or it'll be posted. And I guess I'll take questions. Yeah. Oh, I'm sorry.
Hey, this is great, Jim. Thank you for your talk and for emphasizing the value of soil temperature. It's something that probably needs more attention. It's very, very useful for these kind of things. And I just wonder if you have any, back to a kind of a running theme of our conversations, any thoughts about the depths at which the soil temperatures will be informative, and these sort of thermal inertia approaches can be used.
I hope that I get a chance to talk to somebody. Sorry. I hope that I get a chance to talk to somebody and decide which ones. The one I've gone with 5 centimeters because that feels like a nice cozy place, close enough to the surface, but deep enough to represent the surface area. So I picked 5 centimeters. But no, I don't have any real solid ideas about what the more important depths are for the sensors. That's one thing I'd like to find out. Which ride should I go? Should I go left or should I go right? But thank you for that. That's very important. And I didn't mention I used 5 centimeters just because that sounded good. Anybody else?
I have a question too. Let me ask my question first. So EcoStress is a thermal inertia based sensor on ISS. Have you looked at that at all? And Hydrosat is another company. The lead for EcoStress left NAS JPL, and will launch soon a high resolution thermal product
Yeah.
from their constellation.
Yes, I enjoy eco stress a lot. There are some limitations to that as well, and perhaps something I find can inform future versions of that. Yeah, there's a lot of different. There's never too much to be learned about each of the ways that we can find soil moisture. So, but yes, thank you for eco stress is wonderful.
This is just kind of a comment along these lines, and others have, I think, pointed this out before, but um, of course, it is quite possible to measure soil temperature at a very low cost. And one thing that we might consider more is very high resolution depth profiles of soil temperature with just a few soil moisture measurements, because perhaps together that will tell us all we need to know.
Do you have a response or comment as well?
No, everything. Everything's great. That's what would be my overall comment. But yeah, that would probably more quickly define. But again, that would still be a point measurement because you'd have to have those value. If you're going to have six sensors going down the column, it's still at a point. And yeah, until you have a sensor every 500 meters, you're stuck. But that idea is also very informative about the process in general.